Hello again. Welcome back to AP Biology, Semester 2, talking about free energy. And we're still on water fitness and its environment. This is section 3.2, 4 emergent properties of water contribute to Earth's fitness for life, is what we're going to be talking about on today. Cohesion is the first one that we're going to talk about. Cohesive behavior, ability to moderate temperature expansion upon freezing, and versatility as a solvent. Now we know that cohesion is when the water molecules stay close to each other as a result of hydrogen bonding. Collectively, the hydrogen bonds hold the substance together. So that is what we call cohesion. Cohesion is due to hydrogen bonding, which contributes to the transport of water and dissolved nutrients against gravity in plants. And I have right here on the board a picture of cohesion, where the water direction of the water movement is going up. Okay, talking about the water transport in plants, the evaporation from leaves pulls water upward from the roots through water conducting cells. The properties of cohesion and adhesion can cause the tallest trees to transport water more than 100 meters upward, which is equal to the height of the Empire State Building in New York City. Okay, adhesion, the clinging of one substance to another. And adhesion also, the adhesion of water to cell walls by hydrogen bond helps counter the downward pull of gravity. Okay, for cohesion is surface tension. It's measured of how difficult it is to stretch or break the surface of a liquid. This makes the water behave as though coated with an invisible film. I don't know if you ever heard of the insect that is able to walk on water. It was called the water strider. Well, the high surface tension of the water resulting from the collective strength of its hydrogen bonds allows the water strider to walk on the surface of a pond. Okay. All right. I missed something about adhesion. I want to go back for a minute and mention adhesion. I also, right here, where you see the water molecules, it shows the adhesion of the water to the cells by hydrogen bonds helps resist the downward pull. I did mention that, pull of gravity. So basically, adhesion is against, and cohesion brings things together, or it works with something that is going in the same direction. Okay, cohesion is in the same direction or coming together, and adhesion is the opposite. It helps resist the downward pull of gravity. It goes against. All right? I wanted to make that clear, the difference between cohesion and adhesion. All right, moving on to moderation of temperature. Water moderates air temperature by observing heat from air that is warmer and releasing the stored heat to air that is cooler. Water is effective as a heat bank because it can absorb or release a relatively large amount of heat with only a slight change in its own temperature. Okay, heat and temperature. Kinetic energy is related to heat and temperature. meaning that anything that moves has kinetic energy, the energy of motion. So if you're moving, that is kinetic energy. Anything that is still, we know that is potential energy. Heat is a form of energy. For a given body of matter, the amount of heat is a measure of the matter's total kinetic energy due to motion of its molecules. Thus, heat depends in part on the matter's volume. All right? Temperature is a measure of heat intensity that represents the average kinetic energy of the molecules regardless of the volume. Heat passes from the warmer to the cooler object until the two are the same temperature. For the rest of the semester, when we measure temperature, we are going to measure in Celsius. All right, Celsius degrees is what we're going to be using. Okay, at sea level, water freezes at 0 degrees Celsius and boils at 100 degrees Celsius. The temperature of the human body averages 37 degrees Celsius. The temperature of room temperature is about 20 to 25 degrees Celsius. Okay. A calorie is the amount of heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Conversely, a calorie is also the amount of heat that 1 gram of water by 1 degree Celsius. Okay. So it's like, how can I say? I just repeated myself. All right. Let me go back. Talking about the calorie being the amount of heat it takes to raise the temperature of 1 gram of water by 1 degree Celsius. Calorie is also the amount of heat that 1 gram of water releases when it cools by 1 degree Celsius. A kilocalorie, which is 1,000 calories, is the quantity of heat required to raise the temperature of 1 kilogram of water by 1 degree Celsius. There's another term that we need to know about, and it's called joule. Joule is spelled Joule. 1 joule equals 0.2.39 calories. 1 calorie equals 4.184 joules. Right? Now, water's high specific heat. Let's talk about that for a minute. The specific heat of a substance is defined as the amount of heat that must be absorbed or lost for 1 gram of that substance to change in its temperature by 1 degree Celsius. The specific heat of water is 1 calorie per gram per degree Celsius, abbreviated as 1 CAL/G/degrees Celsius, capital C. Water will change its temperature less when it absorbs or loses a given amount of heat. Heat must be absorbed in order to break down hydrogen bonds, and heat is released when hydrogen bonds form. This is the reason coastal areas generally have milder climates that inland regions do not have. Inland regions, okay? The high specific heat of water also tends to stabilize ocean temperatures, creating a favorable environment for marine life. Earth keeps temperature fluctuations on land and in water within limits that permit life. Also, because organisms are made primarily of water, they are more able to resist change in their own temperature than if they were made of liquid with a lower specific heat. Oh my goodness. Don't do that. Okay. Did it go off? It's still going. Okay. I thought it had stopped. Okay. Okay. So let's talk about evaporative cooling. This transformation from a liquid is a gas to a gas is called evaporation or vaporization. Heat of vaporization is the quantity of heat a liquid must absorb for 1 gram of it to be converted from the liquid to the gaseous state. To evaporate 1 gram of water at 25 degrees Celsius, about 580 calories of heat is needed, nearly double the amount needed to vaporize a gram of alcohol or ammonia. Water's high heat of vaporization is another emergent property caused by hydrogen bonds, which must be broken before the molecules can make their exodus from the liquid. This evaporative cooling occurs because the hottest molecules also I forgot to mention about liquid evaporating. As liquid evaporates, the surface of the liquid that remains behind cools down. Okay? So this evaporative cooling occurs because the hottest molecules, those with the greatest kinetic energy, are the most likely to leave a gas. It is as if the 100 fastest runners at a college transferred to another school. The average speed of the remaining students would decline. Evaporative cooling of water contributes to the stability of temperature in lakes and ponds, and also provides a mechanism that prevents terrestrial organisms from overheating. Okay, now we're going to talk about the insulation of bodies of water by floating on ice. Water is one of the few substances that are less dense as a solid than as a liquid. While other materials contract when they solidify, water expands. At temperatures above 4 degrees Celsius, water behaves like other liquids, expanding as it warms and contracting as it cools. As the temperature falls to 0 degrees Celsius, the water becomes locked into a crystalline lattice. The hydrogen bonds keep the molecules at arm's length, far enough apart to make ice about 10% less dense. 10% fewer molecules for the same volume than liquid water at 4 degrees Celsius. Water reaches its greatest density at 4 degrees Celsius and then begins to expand as the molecules move faster. The hydrogen bonds are constantly breaking and reforming. If ice sank, then eventually all ponds, lakes, and even oceans would freeze solid, making life as we know it impossible on Earth. Okay. Now, let's go to the solvent of life. A liquid that is completely homogeneous mixture of 2 or more substances is called a solution. The dissolving agent of a solution is the solvent, and the substance that is dissolved in the solute is the solute. In this case, water is the solvent and sugar is the solute. An aqueous solution is one in which water is the solvent. Water is a very versatile solvent, a quality we can trace to the polarity of the water molecule, which is what? H2O. The sphere of water molecules around each dissolved ion is called a hydration shell. A compound does not need to be ionic to dissolve in water. Many compounds made up of non-ionic polar molecules, such as sugars, are also water soluble. Such compounds dissolve when water molecules surround each of the solute molecules, forming hydrogen bonds with them. Okay, since we're talking about that, let's go on to hydrophilic and hydrophobic substances. Any substance that has an affinity for water is said to be hydrophilic. From the Greek hydro, which is water, and philios, loving. So water loving. In some cases, substances can be hydrophilic without actually dissolving. For example, some molecules in cells are so large that they do not dissolve. Instead, they remain suspended in the aqueous liquid of the cell. Such a mixture is an example of a colloid, a stable suspension of fine particles in a liquid. An example of a colloid would be Italian dressing, water and vinegar. Okay. Another example of a hydrophilic substance that does not dissolve is cotton, a plant product. Cotton consists of giant molecules of cellulose, a compound with numerous regions of partial positive and partial negative charges that can form hydrogen bonds with water. Substances that are non-ionic and non-polar, or for some other reason cannot form hydrogen bonds, actually seem to repel water. These substances are said to be hydrophobic, from the Greek phobos, fearing. So, water fearing. An example from the kitchen is vegetable oil, which, as you know, does not mix stably with water-based substances such as vinegar. The hydrophobic behavior of the oil molecules results from a prevalence of relatively nonpolar bonds. In this case, bonds between carbon and hydrogen, which share electrons, are almost equally. Hydrophobic molecules related to oils are major ingredients of cell membranes. Imagine what would happen to a cell if its membrane dissolved. Oh my. It's okay. Solute concentration in aqueous solutions. Okay, we know the mass of each atom in a given molecule. So we can calculate its molecular mass, which is simply the sum of the masses of all the atoms in a molecule. Just as a dozen always means 12 objects, a mole, M-O-L-E, represents an exact number of objects. 6.02 times 10 to the 23rd, which is called Avogadro's number. Because of the way in which Avogadro's number and the unit Dalton were originally defined, there are 6.02 times 10 to the 23rd Daltons in 1 gram. The practical advantage of measuring a quantity of chemicals in moles is that a mole of one substance has exactly the same number of moles as a mole of any other substance. Molarity is the number of moles of solute per liter of solution. Okay, and that concludes our lesson on today on the 4 emergent properties of water, which contributes to Earth's fitness for life, which are cohesion, adhesion, temperature, specific heat. And we will talk later. The next time we come together, we will talk about acidic and basic conditions which affect living organisms. Ta-ta!